Hi everyone, my name is Shen. I come from the University of Bristol Smart Internet Lab. Today I'm glad to be here and share our latest work titled In NetMind, Adaptive Radio Access Network Baseband Function Placement by Graph Convolutional Neural Network Encoding and Maid-Solving Deep Reinforcement Learning. This work is supported by UK-funded projects, Reza and Tutor. I will introduce this work following the introduction and motivation, problem formulation, NetMind, results, and conclusion. Firstly, I want to introduce the centralized run, which was very famous in the fourth generation communication networks. In the C run, the request need to go through a remote radio unit and a baseband unit to get access to the service. However, with the emerging of 5G applications, this centralized architecture is no longer able to satisfy the diverse quality of service requirements. In response, 3GPP and other standardizations propose the advanced run, which decentralizes the baseband functions into remote unit, distributed unit, core unit, and user plan function. These baseband functions can be virtualized and distributed on remote access edge computing servers, and the end-to-end communication process is further divided into front haul between RU and DU, mid haul between DU and CU, and back haul between CU and UPF. By dividing the baseband functions, it provides network vendors more flexibility in customizing the network service. In addition, the plug-in design of the baseband functions makes the function migration and scaling much easier, thereby increasing the network scalability. Last but not least, by sharing infrastructure and open interfaces, this design greatly improves the diversity of vendors' ecosystem. However, within the resource-limited edge compute networks, the coexistence of diverse 5G applications and their various X-hole latency requirements might cause higher power consumption and unnecessary resource waste. Therefore, it is important to design an efficient baseband function placement policy to place DU, CU, and UPF on the max. The state-of-the-art solutions are mainly based on mixed integrated linear programming and deep reinforcement learning. However, although MOP can achieve near optimal results, it is very time-consuming and cannot be accepted by 5G. Besides, most of previous IR-based solutions describe a non-Markov decision process which is not theoretically grounded. Also limited by neural networks, DRL lacks generalization capability when applied to different networks or to a network with dynamic structure variations. Therefore, the objective of this work is in twofold. First is to minimize the power consumption of baseband functions in the network, and second is to improve the generalization capability of the algorithm. Taking the left figure example, there are three networks with different architecture. So if we want to have dedicated baseband function placement policy for each of them, we will need 3 optimization sessions. In addition, there might be legacy MAC or upcoming MAC going to be removed or added to the network. This will further diminish the effectiveness of the previously optimized solution. In this case, we firstly mathematically formulate the problem, and the objective function is to minimize the power consumption in terms of the function placement and the routing. Constraint 1 to 3 demonstrate the front haul, mid haul, and end-to-end latency limitations. Constraint 4 and 5 represent the computing resource limitations on the max and bandwidth limitations on the links. To solve this problem and achieve the optimal baseband function placement, we proposed a maze-based DRL, and the environment is shown in this figure, in where each MAC performs as a node, each connection performs as a link, and the 5G core acts as the fixed destination for EMBB and MTC requests, and the destination for URLC can be considered as any node in this maze, as long as it satisfies the latency requirements. This maze design, corresponding to the gaps we mentioned earlier, it enables a manageable action space and aligns to MDP characteristics. Most importantly, it improves the generalization capability by unifying the action space of different networks. In the MDP, the action in each step includes the direction of the next node and also the placement decision. After the agent processes a request, it will process the next one and enter this maze from different entrances. In the end, an episode is deemed to be complete after all the requests has been processed. Then we design the reward in a stepwise manner to guide the agent according to the objective function. And the state information include the remaining computing resources, band resources, the current position, and etc. However, within different networks, the state information will also be changed. This will decrease the generalization performance of the DRL. Therefore, we extend the DRL, and the overall architecture of the NetMind is shown in this figure. Firstly, diverse networks will be converted into diverse mazes. Then the maze information will be extracted and formed into graph-based data. Then this data will be input into a GCN-based encoder and decoder, and the feature in the middle will be further forwarded to train the DRL. The most important component to realize the generalization capability of the DRL is the encoder and decoder. It is used to unify the output length from different graphs. And the inputs of the encoder-decoder includes edge attribute, edge index, and X, which correspond to the bandwidth, distance, connection between nodes, computing resources, location, request information, respectively. Also, when the network changes, it will go through the same procedure. However, instead of training from scratch, we proposed an incremental learning scheme. Firstly, we will train a new encoder and decoder. Then we will reutilize the DRL by inheriting previous knowledge, and we will reset the parameter of the last layer of the neural network. The idea behind this is to allow more freedom to the agent in react to the new environments. The setup of the simulation network is shown in the left figure, and in the first two results, we compare the performance of multiple baseband function placement policies in this network with two different split options. As you can see, in both cases, NetMind can approach the optimal result of the MALP and outperform the other two benchmarks. The bottom left one is the learning performance of the GCN, and the bottom right is the performance of DRL with and without the assistance of GCN. It can be seen that the generalization capability brought from the GCN is not achieved by sacrificing the network performance. The left bottom blue line is the final result of the NetMind, and the upper three are the results when apply DRL to those networks individually. It can be seen that by using NetMind, we can achieve 70% training time savings. And on the right figure, with network variations, we performed an ablation study to evaluate the performance of the incremental learning between resetting the parameter of different layers of neural network before inheriting the knowledge. It can be seen that resetting the last layer and keep the first 2 layers can achieve the optimal result and reduce 50% training costs compared to optimizing from the scratch. So in conclusion, to minimize the power consumption in advanced run while achieving the generalization capability in both static and dynamic networks, we propose the NetMind solution, which includes a maze-based DRL, a graph convolutional neural network based encoder and decoder, and an adaptive layer-wise incremental learning scheme. By NetMind, we can achieve 32% and 41% power savings compared to benchmarks, also 70% and 50% training cost savings. Related code are open source on the GitHub. Thank you for listening. I'm glad to answer your questions.